Okay, so we can start today's session, and I hope I am audible to all of you. Okay, so hi, good evening, and welcome back to this problem solving session for the NPTEL course Geology and Soil Mechanics. So currently we are at the end of week. Yeah. So any problem? Okay, so assuming no such problem, so we can proceed further. So as I was mentioning that currently we are at the end of this week 6, and as we have learned another important aspect, that is in situ stresses. So in this session, we'll mostly solve a few numerical problems regarding this aspect, that are nothing but soil capillarity, negative pore water pressure, and effective stresses. So how to calculate the height of capillary zone, or we can say capillary fringe zone, and what would be the negative pore water pressure, the distribution of negative pore water pressure in that zone, and how to calculate the effective stresses in the in situ soil condition, or in the soil mass at any point, that is the variation of effective steps with depth, that we'll see through a couple of numerical problems in today's session. So it's worth mentioning that this aspect is very crucial for a better understanding of the subsequent topics, such as consolidation, shear strength, and earth pressure, uh, which will be going to learn in the next few weeks. Okay, so with this brief introduction, we'll start solving a few problems. So this is our first problem for this session. So this is related to the determination of effective stress. Okay, so first let me read the problem statement once. The water table is at a depth of 5 meter in a silty soil mass of thickness 10 meter. Laboratory sieve analysis indicates an effective size of the soil mass as 0.015 millimeter. If the void ratio of the soil mass is 0.67 and specific gravity of soil solids is 2.67, now if the silty soil mass as described above is underlain by a clay layer of thickness of 8 meter, what would be the effective stress at the middle of the failure? So this is the main question. So we have to basically find out the effective stress at the middle of the failure. So these are the few assumption or information in addition to the problem statement is given. So assume the silty soil mass to be fully saturated in the capillary fringe zone, and above this zone saturated to a degree of 66%. Properties of the clay layer are given as water content 24%, specific gravity of soil solids 2.62, unit weight of water 10 kilonewton per meter cube, and there is one constant. It's known as Hagen constant. So C. So this the value of C is given as 45 millimeter square. Okay. So first we'll draw the problem definition. So it's given in the problem statement that there is a silty soil mass of thickness 10 meter. Okay. So this is the silty soil mass. Sorry. Having a thickness of 10 meter. Now, below this silty soil mass, there is a clay layer. Okay, so if the silty soil mass as described above is underlain by a clay layer of thickness 8 meter, that means there is one clay layer beneath this silty soil mass, and the thickness of this clay layer is 8 meter. So this is the silty soil mass, and this is clay. Further, the properties of the silty soil mass are given as, that is, the effective size of the soil mass is 0.015 millimeter. So as you know, that effective size is basically denoted by D10, na? So the D10 value is 0.015 millimeter. Then the specific gravity of soil solids is 2.67. Okay, so before that, the void ratio of the soil mass is 0.67. So void ratio E, so this is 0.67. Then specific gravity of soil solids is 2.67. In addition to that, the water table is at a depth of 5 meter in the silty soil mass. So there is one water table. So water table is basically encountered at half of the silty soil mass, mid depth of the silty soil mass. So this distance is 5 meter. So this is the groundwater table. Okay. Now coming to the properties of the clay layer. So these are the properties: W equals to 25%, GS equals to 2.62. So W equals to 0.25 and GS equals to 2.62. Okay, and there is one constant mentioned as C equals to 45 millimeter square. Now the question is, what would be the effective stress at the middle of the clay layer? So we have to determine basically the effective stress suppose this is point A. So this dimension is 4 meter. So at the mid depth of the clay layer, because the clay layer is having a total thickness of 8 meter. So at a distance of 4 meter from the base of the silty soil mass, we have to determine the effective stress, and this is the ground surface. Now the first job for this problem would be determination of the capillary fringe zone. Okay, so if we mention the steps here, so the first job would be determination of AC, that is the height of capillary or capillary height. So this is capillary height. Then gamma bulk and gamma saturated. So this would be for silty soil, and at the same time gamma saturated only for clay, because the clay is under full saturation. If we visualize the problem statement, then this is the water table, this is the water table. So this is the water table. Therefore, below the water table, this half of the silty soil mass and the full clay layer will be fully saturated. This will be under complete saturation. Therefore, for clay, we only need to calculate the gamma saturated. No need to calculate the gamma bulk. Okay. But in case of silty soil mass, so partly means half of the soil mass is under full saturation, and then again above the groundwater table, some part of the soil mass will be under full saturation. That will we'll see, and the remaining portion will be under partial saturation condition. Okay, so that's why we need to calculate the gamma bulk. Okay, now for the third case, for the third step, we need to calculate the total stress at point A, then the pore water pressure at point A, and the difference between these two, or rather we can say the subtraction of UA from sigma A will give you the effective stress at point A. And this is the primary objective of this problem. Okay, so now we'll go step by step. So first we'll calculate the capillary height. So why it's essential to calculate the capillary height? Because we know that due to continuous void spaces inside the soil mass, even above the groundwater table, some soil will be under complete saturation due to the capillary action. Because here in this portion above the water table, so the void spaces will basically act like bundle of tubes of different cross section, and as the diameter of this tube approaches to a very small value, means as the diameter of the tube is basically going smaller, so due to surface tension the water will basically rise to a greater height, and this phenomena is called capillary action. Now this height is basically denoted as AC, is nothing but the capillary height. Now this action, due to this capillary action, the soil mass even above the groundwater table will be under complete saturation up to some distance, up to a distance of AC. So therefore the calculation of AC is very very essential. Now how we can calculate? Okay, that we'll see. So first we can calculate okay. So first of all, we can calculate from the very fundamentals. Okay. So equating the forces in the vertical direction. But if such data is not available, then we have to go for some empirical relationship. For example, Hazen provided an empirical relationship for the calculation of AC, and this empirical relationship is nothing but AC equals to C by E times D10. Okay, here C is the Hazen's constant, so this is the Hazen's constant. E is the void ratio, and D10 is the effective size. Now for the silty soil mass, we know all these parameters. The Hazen's constant typically lies in between 10 to 50, and for this problem it's given as 45 mm square. When the void ratio of the silty soil mass is given as 0.67 and the effective size of the silty soil mass is given as 0.015 millimeter. Therefore, if we substitute these values in this equation, in this empirical relationship, then we can easily obtain the height of capillary rise or height of capillary fringe zone. Okay, so now we'll substitute these values. So C is basically 45 and E is basically 0.67, and the effective size of the silty soil mass is 0.015 mm square. So whatever AC will get after calculating this value, So that will be in millimeter. Okay, so if we calculate, so it would be 45 divided by 0.67 into 0.015, that means 4477. So in terms of meter, approximately this value is 4.5 meter. So the groundwater table is located at a depth of 5 meter from the ground surface, but due to uh, practically the soil mass which is below this water table will be under complete saturation, and due to the capillary fringe zone, soil mass up to a height of 4.5 meter even above the groundwater table will be under complete saturation. So this AC value is coming as 4.5 meter. So if we deduct this 4.5 meter from this 5 meter, so it will be 0.5. So remaining 0.5, it will be under partial saturation condition. Okay. So this part, though this figure is not in scale, so this soil mass will be under partial saturation. So this is under partial saturation. And what is the degree of saturation for this portion of soil mass? So the degree of saturation is 66%, because it's given directly in the problem that assume the silty soil mass to be fully saturated in the capillary fringe zone, and above this zone saturated to a degree of 66%. So this silty soil mass portion, so this portion will be under complete saturation. So here the A's value would be 1, but for this portion the A's value would be 0.66. Okay, so therefore for the silty soil mass, calculation of both bulk unit weight and the saturated unit weight are necessary, whereas for clay only the calculation of saturated unit weight is essential, because here the full clay layer is under complete saturation. However, for the silty soil mass, some portion is under complete saturation and some portion is under partial saturation. Now, how much portion is under complete saturation, that we have already determined through the calculation of capillary fringe zone, and the remaining portion will be under partial saturation. Partial saturation in the sense saturation to a degree of 66% as mentioned in this problem statement. Okay, so our first step is done. Now we'll moving forward. So this was the first step. Now we'll move forward. So for the second step, we'll calculate the bulk and saturated unit weight of the silty soil mass first, and then we'll calculate the saturated unit weight of the clay. So for silty soil mass, the bulk unit weight, so gamma bulk, it would be GS plus AC divided by 1 plus C multiplied by gamma W. So this expression we have got from the basic three-phase relationship. Now for the silty soil, what is the value of GS? So it's 2.67. Then E, it's 0.67. Gamma W, we can take it as 10 kiloton per meter cube. It's also mentioned in the problem statement. And what's about S? So for bulk, the S value will take it as 66%. So we'll substitute these values in this expression. So 2.67 plus 0.66 multiplied by 0.67 divided by 1 plus 0.67 multiplied by 10. Okay, so if we calculate, so 2.67 plus 0.66 into 0.67 divided by 1.67, So it will give us 18.64 as the bulk unit weight of the silty soil mass for a thickness of 0.5 meter. So this is 5 meter. So this is 5 meter. This is 4.5 meter. So remaining portion is 0.5 meter only, because the total thickness of the silty soil mass is 10 meter. Now we'll calculate the saturated unit weight for the silty soil mass. So again, we are calculating for the silty soil. So saturated unit weight, it would be simply Gs plus E by 1 plus E, because here S becomes 1. So 2.67 plus 0.67 divided by 1 plus 0.67 multiplied by 10. So if you calculate, the value would become 20 kilonewton per meter cube. Okay. And coming to the clay layer, so as I have mentioned that for this only we will calculate the saturated unit weight, because it's under complete saturation, and these are the properties. Okay, so the void ratio value is not directly given to this problem, rather the water content or specific gravity of soil solids is given, so therefore we can easily calculate the E. So first we have to calculate the E value. So if we calculate here the E value, so the E value for clay, it will be 0.25 multiplied by 2.62. Okay, because we know that WGS equals to AC, and for complete saturation the value of S becomes 1. So therefore E clay 0.25 into 2.62. 0.25 into 2.62, it will be 0.655. So this is for clay. Now we'll substitute here. So first the specific gravity of soil solids is 2.62. 2.62 plus 0.655 divided by 1 plus 0.655 multiplied by 10. 2.62 plus 0.655 divided by 1 plus 1.655. So it's 19.79 kilonewton per meter cube. Okay. So now we'll moving further for the third step. So for the third step, now we'll calculate the total stress first. So total stress at the mid depth of this clay layer, that is point A. So total stress would be the multiplication of the unit weight and the corresponding thickness. So we'll start from the ground surface. So for the initial 0.5 meter, since the unit weight and the unit weight for this thickness are different, okay, so that we'll have to be very careful. So for the initial 0.5 meter, there is a bulk unit weight and it's 18.64. Then for the remaining 4.5 meter plus 5 meter, the saturated unit weight is 20 kilonewton per meter cube. And then the 4 meter clay, the saturated unit weight is 19.79. So you have to multiply the unit weight with the corresponding, means the thickness with the corresponding unit weight, to get the total stress at that point, up to that point. Okay, so we'll start from the very beginning. So calculation of sigma will be like this, that initial 0.5 meter, which is partially saturated, the unit bulk unit weight is 18.64. So 18.64 multiplied by 0.5 plus this 4.5 meter, this is under complete saturation, and this 4.5 meter is also under complete saturation, and the unit weight is 20 kilonewton per meter cube. Sorry. So as a whole, 4.5 plus 5, that is, sorry, first let me write the unit weight. So 20 multiplied by 4.5 plus 5. This is up to the base of the silty soil mass. Okay, but we have to calculate the effective stress at point A, which is at a depth of 4 meter from the base of the clay. So we'll have to again go down by a depth of 4 meter. Now for this 4 meter, the unit weight is different. So this unit weight is saturated unit weight of the clay, and that is 19.79. So 19.79 multiplied by 4. So this will give you the effective stress at point A. So at this point. Okay, so please calculate. So this value I hope 18.64 into 0.5 plus 9.5 into 20 plus 19.79 into 4. So 278.48. So 278.48 kilonewton per meter square. Now you know that the effective stress is basically total stress minus pore water pressure, because total stress is a summation of effective stress plus pore water pressure. So therefore effective stress you can get by subtracting the pore water pressure from the total stress. Now total stress already we have calculated, so the remaining calculation is the calculation of pore water pressure at that point. Now what would be the pore water pressure at that point? So for that we need to know the variation or distribution of pore water pressure. Okay, so this is the groundwater table. So this is the groundwater table. So it will linearly vary. So the pore water pressure, it will linearly vary, and this pore water, this distribution will be positive, compressive, while in the capillary fringe zone, the pore water pressure would become negative. Okay. So this is negative, this is positive. So therefore, at this location, the pore water pressure will be gamma W into Z, and Z is basically measured from here. Okay, or rather we can say this is measured from here. So now what is the Z value? The Z value is 5 meter plus 4 meter, that is 90 meter. So UA, so UA, UA, so this is 10 multiplied by 4.5 plus 4. Oh, sorry, 5 plus 4. So that means 90 kilonewton per meter square. Therefore, sigma A prime, it would be 278.48 minus 90. So it would be 188.48 kPa or kilonewton per meter square. So this is the okay. Okay, so please remember one point that uh, so far we have calculated the effective stress at the mid depth of clay layer. However, if the question was asked for the calculation of effective stress in this capillary fringe zone, then please be careful that here the effective stress would be total stress plus pore water pressure. Why? Because the pore water pressure in this region becomes negative. Okay, tensile in nature. So therefore minus of minus UA, that would become plus UA. Okay, so therefore the distribution of pore water pressure to have an in-depth knowledge of the pore water pressure distribution is very very essential. So in the capillary fringe zone, the pore water pressure has to be added with the total stress because of its tensile nature or negative nature, whereas for the portion under groundwater table, the pore water pressure has to be subtracted because it's compressive in nature. Okay, so far we have calculated the pore water pressure or effective stress below the groundwater table, so that's why we have to subtract. Otherwise, if we calculate it in the capillary fringe zone above the groundwater table, in that case we have to add the pore water pressure. Okay, so anyhow we can easily calculate the distribution of effective stresses starting from the ground surface itself. So we can basically get the effective stress at any point, at any depth inside the silty soil mass or the clay layer from the ground surface. Okay, so this was the question for the calculation of effective stress at the middle of the clay layer, and we have obtained the value as 188.48 kPa or kilonewton per meter square. So to obtain the answer, the first step was the calculation of capillary height based on the empirical relationship given by Hagen. Then the calculation of unit weight bulk and saturated for the silty soil, and only the saturated unit weight for the clay. And then we have calculated the total stress first at the middle of the clay layer, pore water pressure at the middle of the clay layer, and then we have subtracted the pore water pressure from the total stress, and thus we have got the effective stress at the middle of the clay layer. Okay, so I hope there should not be any problem or confusion up to this part. So if so, then we can move on to the next problem. Okay, so the next problem is a this is very similar to the previous problem. Nothing to do with this problem except the calculation of the capillary fringe zone is not required in this problem. Why? Because it's directly mentioned. Okay, so for that we'll read the problem statement first. So at a particular site there lies a layer of fine sand 6 meter thick below the ground surface and having a void ratio of 0.72. The groundwater table is at a depth of 3 meters below the ground surface. The average degree of saturation of the sand above the capillary fringe is 55%, and the soil is saturated due to capillary action to a height of 1.5 meters above the groundwater table. Okay, so assuming GS equals to 2.62, calculate the total effective pressures at depth of 4.5 meters below the ground surface. So again, if we uh, draw the problem definition, so this is the 6 meter thick sand, 6 meter thick fine sand, and the water table is at a depth of 3 meter. So this is the water table location. So this is at a depth of 3 meter, and above this water table the capillary zone or the capillary action is valid up to a height of 1.5 meter. So this distance is 1.5 meter. Okay, and for remaining 1.5 meter, so here your S equals to 1, but here your S value is 0.55 only. Okay, then the void ratio is given as 0.72 and GS value is given as 2.62. And at what location we have to calculate the effective pressure? So the effective pressure we have to calculate at a depth of 4.5 meter below the ground surface. So this is 3.5 meter. So we have to go down by 1.5 meter. So suppose here we have selected a point A, and at this point we have to calculate the total effective pressures. So again we'll start from the calculation of bulk unit weight and saturated unit weight, because the capillary fringe zone calculation, the height of capillary action is not required, it's directly given to this problem. So we'll calculate first the gamma bulk. So gamma bulk, it will be 2.62 plus the degree of saturation is 0.55 multiplied by E value is 0.72 divided by 1 plus 0.72. This multiplied by gamma W, that is 10. So this will give you the gamma bulk. So it's a 17.53 kilonewton per meter cube, and gamma sat, so it's 2.62 plus 0.72 divided by 1 plus 0.72 into 10. So it's 19.42 kilonewton per meter cube. Okay, so now we'll calculate the total stress at point A. So sigma A, it will be gamma bulk multiplied by 1.5, because 1.5, this 1.5 meter is under partial saturation. So 17.53 into 17.53 into 1.5. Now the remaining portion is under complete saturation, so therefore 19.42 multiplied by 1.5 plus 1.5. So this will give you the total stress at point A. So this is 1.5 and this is 1.5. This 3 meter will be under complete saturation or full saturation. So this value 17.53 into 1.5 plus 19.42 into 6, 17.53 into 1.5 plus 19.42 into 3. So this is 84.56 kilonewton per meter square. And for UA, so UA, so this will be, so here the distribution will look like this, that so below the water table, so water from the water table, so it will start a value 0 and gamma W, so this is plus, and for the capillary fringe zone it will be negative. Okay, so this is measured as Z. Now for this problem the Z value is 1.5. So 10 into 1.5, that is 15 kilonewton per meter square. So obviously the sigma A prime would be 84.56 minus 15. So it's 69.56. Okay, so prime indicates effective stress or effective pressure. So this is the answer. So it's a very identical problem to the first one. So The only exception is that uh, in the previous problem we had to first calculate the height of capillary fringe or capillary action based on an empirical relationship given by Hazen, but in this problem there is no such need because the capillary fringe height itself is given to this problem. So this problem is a more simplified version of the previous problem. Okay, so any confusion, any doubts up to this portion? Again, in both the cases, we are calculating the effective pressure under the groundwater table or below the groundwater table. So if we calculate the effective stresses in the capillary fringe zone, then we have to be very careful that in that zone the effective pressure would be tensile, so pore water pressure would be tensile in nature, and then the pore water pressure will be additive to the total stress to get the effective stresses. Okay, so assuming there is no problem from your end, so we can take the next problem. In the next problem, a clay layer of 4.5 meter thick with gamma saturated 22 kilonewton per meter cube is overlain by a 3.5 meter sand with gamma saturated 18 kilonewton per meter cube and gamma dry 15.5 kilonewton per meter cube. The top of this layer being the ground surface, the water table is located 2.5 meter below the ground surface. The clay layer is underlain by a sand stratum that is in artesian conditions with the water level in a standpipe being 5 meter above the ground surface. Calculate the effective vertical stresses at the base of the clay layer. So as you can visualize from this problem statement that there is a clay layer of thickness 4.5 meter. So this is the clay layer of thickness 4.5 meter, and this layer is sandwiched between two sand layers. So this is one sand layer and this is another sand layer. And the water table location is at a depth of 2.5 meter. Okay. So this is the water table location. And this distance is 2.5 meter. Now, the saturated unit weight of the sand is given as, so sorry, for clay it's given as 22 kilonewton per meter cube. For sand, the saturated unit weight is given as 18 kilonewton per meter cube, and the dry unit weight is given as 15.5 kilonewton per meter cube. Okay, So the dry value is given for this portion, the sand above the water table. Okay, and below the water table, we'll use the saturated unit weight. Since the water table is encountered inside the sand at a depth of 2.5 meter from its top, so therefore the portion which is above the groundwater table, will use the dry unit weight for this portion, and the portion which is below the groundwater table, for that will use the saturated unit weight, which is 18 kiloton per meter cube, as given to this problem. And for clay, since it's under full saturation, so we'll only use the saturated unit weight as 22 kilonewton per meter cube. Now, sorry. Now we have to calculate the effective vertical stresses at the base of the clay layer. Sorry. So you have to calculate, suppose at this point, this is point A and this is the base of the clay layer. So this point, we have to calculate the effective vertical stresses. And one more information is available for this problem, that is if we insert a stand pipe in the sand stratum, that is the lower sand stratum, not in the upper sand stratum. So this sand stratum is in artesian conditions with the water level in the pipe being 5 meter above the ground surface. So this information, please be very careful about this information, because uh, you have to basically appropriately address this information while calculating the effective vertical stress at the base of the clay layer. So this is nothing but that suppose this is the standpipe. So the water level will be 5 meter above the ground surface. Okay, so again this is not in scale. So this statement, for this statement, you have to be very careful and you have to be appropriately addressed in the calculation procedure. So first we'll start with the calculation of total stress, then pore water pressure, and followed by the effective stress. Okay. So the calculation of F total stress, so at point A, sigma A, so this will be simply the multiplication of thickness and corresponding unit weight, that is gamma z. So for this 2.5 meter, so we'll use the dry unit weight as mentioned earlier, so 15.5 into 2.5, so 15.5 into 2.5. And for the remaining 1 meter, so sorry, 1 meter, because the total thickness of the sand is 3.5. So for the remaining 1.5, so we'll use 18 kilonewton per meter cube. So 18 into 1.5 plus, since we are calculating the vertical effective vertical stress at a total stress at the base of the clay layer, so this 4.5 meter multiplied by 22. So 22 multiplied by 4.5. So it's 164.75. Sorry, I made a mistake here, because if this is 2.5, then the remaining portion of the sand is having a thickness of 1 meter, because 3.5 minus 2.5, that will be 1, not 1.5. Okay, so please note a correction here. So it's 1. So that means the total stress value would be 155.75 kilonewton per meter square. And for the calculation of pore water pressure at point A, since the jet will start from here, so it will be gamma w into z. So the z value for point A is 1 plus 4.5. Sorry, this is not this is 4.5, so 5.5. So so 5.5. But please keep in mind that the for the artesian condition, so this is the tricky part for this problem. For the artesian condition, the water table rises 5 meter above the ground surface. So as if the pore water pressure here would be for a height of 5 plus the entire thickness of the sand and clay. So that means a 5 total. So this the thickness of sand and clay as a whole is 3.5 plus 4.5, that is 8 plus 5. So this much pressure will act at pore water pressure will act at point A due to the artesian condition. If there is no artesian condition, then this will be simply 1 plus 4.5, that is 5.5. However, due to the artesian condition, the pore water pressure will be greater than the actual value, and it will be having a value of 5 plus 8. Okay, so how we are getting 5 plus 8? So because this 5 meter is above the ground surface, the water table rises above the ground surface up to a height of, or by a height of 5 meter, and this is the total thickness of the sand and clay, 3.5 plus 4.5. Okay, and this multiplied by 10. So that means 8 plus 5, that is 13, into 10, that is 130 kilonewton per square. So obviously the effective stress would become 155.75 minus 130 equals to 25.75 kilonewton per meter square, and this is the answer. So this is the tricky part. For that, you have to be very careful that due to the artesian condition, the pore water pressure will deviate from its actual value. Okay, and this is applicable only at the base of the clay layer and inside the lower sand layer. Now, if you suppose go for the calculation of effective stress in this lower sand layer, or at any location except the base in the clay layer, then it will be the usual value. Means you have to calculate the z from this groundwater table location and multiply that z with the unit weight of water to calculate the pore water pressure at that level. And for sand above the groundwater table, the pore water pressure will be simply 0. Okay, so if we draw the pore water pressure distribution, so this will be I think this value will be more than 55, so this will be 130. So this was 55 if there is no artisan condition, but due to the artisan condition, this value would become 130. Yeah, so if we draw the, sorry, this is 10, so this gradient will not be, this is 130, and it will follow. Okay, so this is 130. So above the base, it will be simply what about you are getting gamma W and Z, but starting from the base, it will be due to the artesian condition, because the lower sand stratum is under artesian conditions with with the water level in the standpipe being 5 meter above the ground surface. Okay, so next we'll solve one problem which was basically asked in GATE examination 2016. So in this problem, a seepage flow condition is shown in the below figure, and the saturated unit weight of the soil gamma sat is given as 18 kiloton per meter cube. Now using the unit weight of water as 9.81 kiloton per meter cube, the effective vertical stress on plane XX you have to determine. Okay. So we can solve this problem by two different approaches. So we'll see those approaches one after another. So first approach one. Okay. So in this approach, you have to just recall the variation or the analytical form or expression of the effective stress due to different seepage condition. So as we have seen in this lecture or in this week, that there are three different conditions: when there is no seepage flow inside the soil mass, then when is seepage flow in the downward direction, and the third condition is when there is a seepage flow in the upward directions. Now depending on these three conditions, the effective vertical stress will basically vary inside the soil mass. So if there is a seepage flow in the downward direction, then the effective vertical stress will basically increase as compared to when there is no seepage flow condition. And in the opposite case, when there is a seepage flow in the upward direction, the effective vertical stress will decrease compared to when there is no seepage flow condition. Now, what is the analytical form? So, the analytical forms are, so when there is no seepage flow, so it will be simply gamma prime multiplied by Z. Here gamma prime is the submerged unit weight, and Z, this is the distance at which we are measuring the effective stress from the top surface of the soil. Suppose this is the top surface and this is the Z. And when the flow is basically occurring in the downward direction, then for this problem it will be gamma prime Z plus I gamma W Z. So this is for the seepage flow in the downward condition. This is no flow. And for the upward seepage, so this will be gamma prime Z minus I gamma W Z. This is for the upward seepage flow. So it's very obvious that the effective stress is basically increased when there is a seepage flow in the downward direction, and the effective stress is getting decreased when there is a seepage in the upward direction. And what is the quantity by which the effective stress is increased or decreased? The quantity is I comma W into Z. Okay, and we can prove that this is coming from the seepage force which we are getting in the direction of flow. Okay, so that is not the concern, at least for this problem. So for this problem we have to calculate the effective vertical stress on plane xx, which is basically located at a depth of 5 meter from the top surface of the soil. Okay, so first we'll identify for this problem what is the condition or which condition is valid for this problem. So no flow, or the seepage in the downward direction, or seepage in the upward direction. So as we can see, suppose if we basically choose 3 points, so this is point A, and 2 points, and this is point B, that is at the top and bottom of the soil sample. Then at the top of the soil sample, as you can see, the head is, the total head is, and if we basically choose this is as the datum, so this is as the data. So total head for point A, it is 3 plus 1 plus 5, so plus 1. So this is the datum head and this is the pressure head. So pressure head is 4 meter and the datum head is 6 meter. So as a whole, the total head at point A is 6 plus 4, that is 10 meter. And on the other side, the total head at point B, so the datum head is 0. And what is the water head? So the, or pressure head, so it's 2 plus 1 plus 5 plus 1, that is your 1 plus 5 plus 1, that is your 7 meter. So it's lower than the head, total head at point A. So we have first identified the total head at point A and the total head at point at point B. And as you can see, the total head at point A is greater than the total head at point B. So this is 7 meter and this is 10 meter. Okay. So therefore, the flow is basically taking place in the downward direction. So in the downward direction, the seepage flow is taking place. So this is the appropriate case for this problem. So gamma prime z plus I gamma w into z. So we can write the analytical expression for the effective stress at plane xx. Suppose this is indicated by sigma xx prime. So it will be your gamma prime z plus I gamma w z, since your flow is basically taking place in the downward direction. So this is the seepage flow direction. So this is very crucial. So identification of the seepage flow direction is very crucial to answer this question. So if you identified the seepage flow direction in a wrong way, then you will be ending up with some wrong results. Okay, so therefore you have to be very careful about the seepage flow direction, and it will be governed by the total head at the top and bottom of the soil. So if the total head at the top is greater than the total head at bottom, then obviously flow will take place from higher total head to lower total head. Okay, so that means in the downward direction. Otherwise, if the total head at the bottom is greater than the total head at the top, then the seepage flow will be taking place in the reverse direction, that is in the upward direction. Okay, but this is not the case for this problem. So for this problem, the seepage flow is basically taking place in the downward direction. Therefore, uh, the expression of the effective stress at any section xx would become gamma prime z plus I gamma w z. Now we'll figure out the values. So z for xx plane is basically 5 meter, and this gamma prime. What is gamma prime? Gamma prime, this is a submerged unit weight. So submerged unit weight, as you know, it's nothing but the saturated unit weight minus the unit weight of water. So saturated unit weight for the soil given is 18 kilonewton per meter cube, and the unit weight of water is given as 9.81. Okay, so 18 minus 9.81, so it's 8.19 kilonewton per meter cube. And uh, I, so I is the hydraulic gradient. So hydraulic gradient is nothing but head lost uh, divided by the length over which the head is lost. Now, how much head is basically lost over this soil sample? So the head loss is HA minus HB. So that is 10 minus 7. So if we write it here, so I is basically delta H by L, and delta H is nothing but HA minus HB divided by L. So HA is basically 10 and HB is 7 and your L is 6. So 3 divided by 6, that is half. Okay. So in this way, we have calculated all the parameters which are involved in this equation, that is Z, gamma prime, and I. Now we can easily calculate the sigma xx prime. So sigma xx prime, so it would be uh, gamma prime into Z, that is 8.19 into 5 plus I gamma w. I is your half, gamma w is your 9.81 into Z. Z is again 5. 8.19 into 5 plus 0.5 into 9.81 into 5. So 65, it's 65.48 kPa or kilonewton per meter square. So this is the answer. So this value we are getting by approach 1. Now we'll see the application of approach 2. So we can again calculate this effective stress on the plane XX by a different way. Okay, so that we'll see. So for that, we'll first determine the distribution of total head, elevation head, and the pressure head uh, throughout the soil sample, throughout the length of the soil sample. So this is the length of the soil sample. So if we mark it here, so this is point A, that is the top of the soil sample. This is point B, bottom of the soil sample, and this is the length of the soil sample. Okay, and this is the reference for calculating Z, and this is the data. Okay, so now we'll calculate the same thing, that is the total effective stress at the XX level but by a different way or different approach, and we'll compare whether we are ending up with the same result or not. Okay, so frankly speaking, we should have the same answer whatever the approach is. Okay, so the approach is immaterial. So if we approach if we consider approach 2, we should have the same value for the total effective stress at the elevation xx. So approach 1, this is nothing but that you have to recall the analytical expression, or rather you can derive this expression from the fundamentals, and then you have to substitute the values, appropriate values for submerged unit weight, the value, the depth at which we are calculating the effective stress, then the hydraulic gradient, unit weight of water, etc. And for approach 2, we have to first establish the valuation of total head, elevation head, and pressure head throughout the length of the soil sample. That we'll see. Okay, So one more thing, if you ask me about this analytical expression, that how it basically how we have arrived at this expression. So for that, I'll request you to go through the lecture materials which are uploaded in the online portal. So you will be having a better understanding for the expression. So what is the derivation procedure for this expression? Okay, so at least for this problem solving session, I am not going into that details of the derivation. So you can easily get into the derivation, the complete derivation for this expression in the lecture materials which are released in the course portal. Okay, so we'll then straightly move on to the approach 2. So in this approach, as I have mentioned, that we'll first establish the variation of total elevation rate and the pressure rate throughout the soil sample. So we'll basically pick three sections or 3 points for the given soil sample. So first, this is point A, that is that indicates the top surface of the soil. Then section XX, okay, so at which we have to calculate the effective vertical stress, and point B, that indicates the bottom of the soil sample. Now, what is the elevation height for all these section or points? What is the elevation height? So the elevation height, if this is the datum, then for point A, it's 5 plus 1, that is 6 meter. For section XX, it's 1 meter, and for point B, it's simply 0. Okay, so it's directly lies on the datum. And what is total height? So total height, so this is elevation height and this is total height, and then we'll calculate the pressure height. Okay, so for total height, as you can see that for point A, it's 1 plus 5, that means 6 plus 1, 7 plus 3, 10. So it's 10. And what's about B? So for B, it's 1 plus 5 plus 1. So that means 7. Now, if we, as you know, that the total height is a summation of elevation height, pressure height plus velocity height. Now, for flow through soils, the velocity height is very, very negligible, so we can neglect. So, in the very beginning, we have discussed about this, and the total height now becomes a summation of elevation height and the pressure height. Therefore, if we deduct the elevation height from the total height, then we can easily get the pressure height. So 10 minus 6, so the pressure height is 4, and for point B, the pressure height is 7 minus 0, that is 7. Okay. Okay. So now what is the total head at point at elevation XX? So the total head, the head is basically reducing. So the head is basically reduced from a value of 10 at the top of the soil sample to a value of 7 meter at the bottom of the soil sample. So therefore the head loss delta H, this is basically 10 minus 7, that is 3 meter, and this head is lost over a length of 6 meter. So therefore your hydraulic gradient I, this is nothing but 3 by 6, that is half. Now how much distance we have covered or we have traveled from point A to section XX? So we have basically traveled a distance of 5 meter from point A to section XX. Therefore, ideally, the total height at this elevation XX should become 10 minus, so this is the rate, by which the head is basically lost, and this is the distance 5. So therefore the total head at this elevation becomes 10 minus 2.5, that is nothing but 7.5, and the elevation is 1, that means 7.5 minus 1, so that will give you 6.5. This is the pressure head. Okay, so pressure head is nothing but H minus HE. So this is HE, and this is H, and this is your HP. So in this way, we have basically got the elevation head, total head, and pressure head for all three sections. Passing through point A, passing through point B, and the section XX itself. Now, this pressure head multiplied by unit weight of water, that is simply nothing but the pore water pressure at that level. So if we multiply this pressure head with the unit weight of water, so that will simply represent the pore water pressure at that level or at that point inside the soil mass. Now from the very fundamentals, your sigma xx prime should be total stress minus the pore water pressure. Now what is the total stress? The total stress is 3 plus 1. So this is the water head. So 4 plus 1, 3 plus 1. This should be multiplied by the unit weight of water. Okay. And then the saturated unit weight multiplied by the 5, this distance, so that will give you the total stress. So 18 multiplied by 5, so this is the total stress at section XX. And what is the pore water pressure? So pore water pressure is nothing but 6.5. This is the pressure head at section XX multiplied by the unit weight of water, 9.81. Okay. So 9.81 into 4 plus 18 multiplied by 5 minus 9.81 into 6.5. So that means 65.48 kilometer per meter square. So this is the value we are getting by approach 2. Now what value we have got by approach 1? So this is again 65.48. Okay. So that means we are getting the same result whatever the approach may be. So if we basically proceed by approach 1, we are getting 65.48 as the total effective stress at an elevation of x at the section XX. Again, if we proceed by approach 2, so we are getting the same result, that is 65.48 as the effective stress at section XX. So for approach 1, you have to recall the analytical expression of the effective stress depending on the direction of seepage flow. So whether the seepage flow is occurring in the downward or upward direction, or there is no seepage flow. So accordingly, you have to recall or memorize the effective stress expression. You have to appropriately substitute the parameters which are involved in that expression. Then you will be ending up with the effective stress at any section. Otherwise, you can first establish the variation of elevation at total and pressure rate throughout the soil sample. Then you can calculate the total stress at the point where the effective stress is required, and you can subtract the pore water pressure from the total stress at that point. Then you can easily get the effective stress at that section. So please be careful, or please keep in mind that the pore water pressure uh, in that section would be multiplication of pressure head and the unit weight of water. Okay. So this is the solution for problem 4. So please let me know if you have any doubts, or if you require further clarification for this problem. So this problem was asked in GATE examination 2016. So you can therefore expect this type of question in the examination. Okay, just give me a few minutes. Okay, so if there is no confusion, or if this is fine from your end, then we can take the last problem for this session. And in this problem, a 6 meter uh, thick a 6 meter thick stratum of fine sand having submerged density of 11 kilonewton per meter cube is basically given. So quicksand condition occurred at a depth of 3.8 meter of excavation. Now, what is the depth of lowering of groundwater table required for making an excavation 4.5 meter deep? Take density of water as 10 kilonewton per meter cube. Okay, so this will be more appropriate if we call it as unit weight instead of density, because the unit of density is kg per meter cube or gram per centimeter cube, whereas the unit weight is expressed in terms of kilonewton per meter cube. Okay, so irrespective of that, so this is the problem statement. So we can visualize the problem statement. So two scenarios are talked about. So first we'll talk about the scenario 1. So this is the total thickness of fine sand. So this is 6 meter, and this is the excavation depth, D1. So this is 3.8 meter. Now for scenario 2, again this is 6 meter, but in this case the excavation depth is increased to a value of 4.5 meter. Okay, so for the first scenario, quicksand condition occurred at a depth of 3.8 meter of excavation, but in the reality we uh, we we'd like to carry on the excavation to a depth of 4.5 meter, to a greater depth. Okay, so for that, what is the depth of lowering of the groundwater table required? So for the first scenario, we are having the quicksand condition when the depth of excavation reached a depth of 3.8 meter. but we can safely carry on the excavation up to a depth of 4.5 meter, or we can omit this word safely. So for making an excavation up to 4.5 meter depth, so what should be the depth of lowering of the groundwater table? So therefore, locating the groundwater table, so it's quite obvious, or as we can understand from this problem statement, that uh, locating the groundwater table, it's very essential to answer this question. So we don't know what is the location of groundwater table in any of these scenarios, means scenario 1 or scenario 2. So therefore, identification of the location of this groundwater table is very essential for this problem. So first we'll assume that this is the groundwater table location from the top surface. Okay, and this is the groundwater table location from the top surface for scenario 2. Now, when quicksand condition occurred, so quicksand condition occurs when the effective stress at the base of the stratum, fine sand stratum, becomes 0. So this is the condition for quicksand condition. Okay. Now, if we consider to point, so this is point A. Suppose this is point A. So quicksand condition occurs when sigma prime A becomes 0. Now we have to first calculate the sigma A prime at that is sigma prime at point A for both the scenarios, scenario 1 and scenario 2. So for scenario 1, the sigma A prime, it would be total stress minus the pore water pressure at that level. So what is the total stress? So total stress would be this thickness. So this thickness is nothing but d minus dE1, and this is d minus dE2. Okay, so gamma sat d minus dE1 minus pore water pressure. So we'll calculate the effective stresses at point A simultaneously for scenario 1 and scenario 2. So sigma A prime, so this is gamma sat d minus d2 minus pore water pressure. Now pore water pressure, so this will be gamma w into z. Now what is the z value? Z value, it would be d minus dW1 for scenario 1, and for scenario 2 it will be d minus dW2. Okay, multiplied by unit weight of water, and that is 10 for this problem. So gamma w d minus dW1, here gamma w d minus dW2. Now this value, we have to equate this value to 0 for the quicksand condition. Okay, so therefore the submerged density is given as 11. So what would be the saturated density? Then saturated density, so gamma sat, it will be gamma sub plus gamma w. Okay, because gamma sub, this is gamma sat minus gamma w, so gamma sat would be gamma sub plus gamma w. So gamma sat, this is gamma sub plus gamma w d minus d1 minus gamma w d minus dw1 equals to 0. Similarly, gamma sub plus gamma w d minus d2 minus gamma w d minus dw2 equals to 0. Now we'll substitute the known values. So for example, the gamma sub is 18, then gamma w is 10. Now not 18, it's 11. Then d is 6, d1 is 3.8 minus 10 multiplied by 6 minus dw1 equals to 0. So from this equation, we can calculate the value of dw1. So it would be 6 minus 21 multiplied by 2.2 divided by 10. And the value would be 6 minus 21 into 2.2 by 10. So that is 1.38 meter. So similarly, we can calculate the dw2 value. So it would be 11 plus 10 multiplied by 6 minus 4.5 minus 10 into 6 minus 4.5 equals to 0. So dw2, it would be, sorry, this is 6 minus 21 into 1.5 divided by 10. So it's 2.85 meter. So we have calculated the location, or we have identified the location of groundwater table for both the cases. So therefore, it becomes very easy to get the lowering. This is the lowering. So this is the lowering, that is delta dw. Okay, so delta dw is your dw2 minus dw1, that is 2.85 minus 1.38, that is 1.7. So we have to lower the depth of groundwater table by an amount of 1.47 meter to make an excavation 4.5 meter deep. Okay, so in the first case, the depth of excavation reported as 3.8 meter when the quicksand condition occurred. However, we would like to make an excavation 4.5 meter deep. So what should be the depth of lowering of groundwater table? So to answer this question, we have individually calculated the groundwater table location for both the cases, that is case 1 and case 2, and then we have taken a difference between the two, that will give you the answer. That is the depth of lowering of the groundwater table. So this is the tricky part. That is the identification of the location of the groundwater table. Okay. So this is also a very interesting problem. So only you need to know the condition for quicksand condition, or the criteria for quicksand condition. That is the effective stress becomes zero when quicksand condition occurs, and this effective stress equation or effective stress at the base of the fine thin stratum you can easily get by subtracting the pore water pressure at that level from the total stress at that level. Okay. And total stress and pore water pressure you can easily calculate from the fundamentals. So this is for problem 5. Now we'll move on to the homework problem. So this homework problem, this is nothing but the previous problem, that is problem 5, but this is framed in a different way. So in this problem, a clay layer 8 meter thick has a unit weight of 16.5 kilonewton per meter cube and is underlain by sand. The top of the clay is the ground surface, and excavation in the clay layer failed when the depth of excavation reached 5 meter from the ground surface. The height to which water would have risen from the top of sand in a borehole if it was drilled into sand prior to the excavation is. So indirectly in this problem as well, we have to basically determine the water table location to answer this question. So if we draw the problem definition, so it would be, so this is the 8 meter clay layer, and this is the 5 meter excavation. When failure occurs, so this is clay, this is sand. Now at this point, suppose point A, when the failure occurs, effective stress becomes 0. Now prior to excavation, if you drill a borehole, then what would be the rise of water in that borehole? So that means indirectly it's asked to determine suppose this distance x. Okay, so this distance is basically required. Suppose this is x. So this is the problem. So similar to the previous problem, you have to first equate this sigma a prime equals to 0, and you know how to calculate this sigma a prime. So this will be the depth, total thickness minus the depth of excavation multiplied by gamma sat. Okay, so gamma sat d minus de, and suppose this is your dw1. So this is minus gamma w d minus dw, so not 1. So this is your de, this is your d. So this will be 0. So from here you have to first calculate dw. So if you want to know dw, then your x would be simply d minus dw. Okay, so this would be the answer. So I'll not solve this problem at its full length. So since this is a homework problem, so I am leaving it up to you. And you please try to solve this problem at your home and let me know if you face any difficulties while solving this problem in the upcoming session. Okay, so this is for today's session. Uh, for your kind information, we'll again meet on 10th March Sunday from 5 p.m. to 7 p.m. So now I'll wait for a few minutes. If you have any specific questions regarding today's session, you can ask me. Okay, and uh, if we try to summarize the entire session, so first we have taken problems to determine the effective stress considering the capillary fringe action. So in the first problem, we had to determine the height of capillary fringe zone based on an empirical relationship given by Hazen. However, in the next problem, the capillary fringe zone thickness or height is directly given. So problem 2 is a simplified version or a simpler version of problem 1, and it becomes more easy for us to calculate the effective stress. So in these two problems, it's very essential to take a note that if we calculate the effective stress in the capillary fringe zone, then the pore water pressure would be tensile in nature. So therefore, it would be additive to the total stresses. However, for calculating the effective stress below the groundwater table, the pore water pressure would be compressive in nature and it would be subtractive to the total stress. Okay, so this is a very important point for the calculation of effective stress at any point inside the soil mass. Now, apart from this problem 1 and problem 2, the third problem, we have also determined the effective vertical stress. However, in this problem, a clay layer is sandwiched between two sand layers, and the bottom sand layer or the bottom sand layer is under artesian conditions with water level in a standpipe being 5 meters above the ground surface. So that's why we have to appropriately address this condition, the artesian condition, with the water level being 5 meters above the ground surface. So the pore water pressure will not be simply gamma W into Z. The Z is basically measured from the groundwater table location. So it will be something else. So you have to basically calculate the total height starting from the base of the clay layer up to the groundwater table location in the standpipe. That is the thickness of upper sand, thickness of clay, plus the height above the ground surface. That will be the pore water pressure at the base of the clay layer. Okay, so this is a tricky part for this problem, else the problem is similar to the previous two. Okay, and in the fourth problem, so we have also determined the effective vertical stress. However, for this problem, seepage flow condition is vital. So you have to first identify the seepage flow condition, whether there is no flow or the flow is occurring in the downward or upward direction. And depending on that, you have to correctly utilize the expression of effective stress. So this is approach 1. There is one more approach, that is approach 2, and in that by using that approach also you can determine the effective vertical stress. So for the first approach, we have to just recall the analytical expression of effective vertical stress, and then you have to appropriately substitute the entities which are involved in that equation, and you can easily get or obtain the effective vertical stress at any section or at a section which is required for that problem. However, for approach 2, you have to first establish a variation of elevation rate, total rate, pressure rate, or specifically the pressure rate, because pressure rate will give you the ultimately will give you the pore water pressure variation, and that is required for calculating the effective stress, because you know effective stress is nothing but total stress minus effective stress, total stress minus pore water pressure. Therefore, a variation of pore water pressure is essential before answering or before calculating the effective stress. So total stress you can calculate from the water head, that is for this problem 3 plus 1 uh, into the unit weight of water, then the saturated unit weight multiplied by the distance at which you are required to calculate the effective stress. So that is total stress minus the pore water pressure. So pore water pressure you can get from the pressure head. So pressure head multiplied by the unit weight of water, that will give you the pore water pressure at an elevation, or at any elevation that is required for the problem. So in that way also you can calculate the effective stress. However, both the approaches will give you the same answer. Okay. And for problem 5, what we have seen that two scenarios were talked about. For the first scenario, when the depth of excavation reached a value of 3.8 meter, quicksand condition occurred. However, would like to make an excavation up to 4.5 meter deep. So what should be the groundwater table lowering, or the depth of lowering for the groundwater table? So that was the question. So for that we have uh, identified the location of groundwater table individually for both the scenarios, and make a deduction between, or subtraction or difference between the two. So that will give you the required depth of lowering for the groundwater table. So this problem is again framed in a different way for the homework problem. So here only one condition is talked about, and the depth of excavation when reached a depth of 5 meter from the ground surface, the clay layer failed. So the saturated unit weight of the clay layer and thickness of the clay layer were given. Now we have to calculate the height to which water would have risen from the tops of the sand in a borehole if it was drilled into sand prior to the excavation. That means indirectly we have to calculate, we have to first locate the groundwater table, and then we have to address this question. So this is all for today's session. Uh, Now, if you require any further clarification, please let me know. I will wait for a few minutes, and then we'll close this session. Thank you. Thank you for joining this session, and have a nice day ahead. हाँ सर, आप फोन किए थे। ओ, अच्छा अच्छा, नहीं नहीं, नहीं नहीं, एक मीटिंग में था। हाँ 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 हाँ, ठीक है, ओके, थैंक यू, हाँ। हम्म। Okay, so as I'm not getting any response from your end, I'm hoping that it's all fine from your side. So I'm closing this session here, and thanks a lot again for joining this session. Hope we'll meet again on next Sunday, that is on 10th March at 5 p.m. Okay, so thank you.